Hello, good afternoon. My name is Giannis Combe. This is Danilo, Delgado, and Sara, Patino, and our project is a test rig for temperature and pressure sensors. Here we have an outline of what we're going to be going through this afternoon. As for the motivation, we had the opportunity to be sponsored by Hardware, a renowned medical company that supplies different places with their instruments and also their research. The point of our project was to provide validity for their sensors to be used in medical applications, uphold the accuracy and the repute of Hardware's products and standards, and lastly, contribute to providing quality of life for their patients with heart conditions or other medical conditions. As for the objective, we need to design a test rig that needed calibration for pressure and temperature transducers, collect experimental data at different temperature and pressure ranges, and create a calibration table for a liquid medium of a pressure range between 0 to 200 millimeters of mercury and in temperature 20 to 60 degrees Celsius. And also support with the data supported with simulations, computational analysis, and lastly, a cost analysis for the company. Here we have our Gantt chart, which is a deadline of most of the tasks that we need to follow. We pretty much met the deadlines by about 85 to 90%. As for our plan of action, we wanted to go through an optimization process of the test rig, through different testing and experimentation, and we wanted to manipulate different factors such as the temperature ranges, pressure ranges, the devices that were going to be implemented, and also the rig configuration. As for the applied knowledge, we use different items that we have learned in our undergraduate classes, such as the equations from thermodynamics, heat transfer, design-wise from Solidworks using the stress analysis, static analysis, and lastly, some static statistical analysis using MATLAB and the DAT system. As for our global awareness, we made sure to go ahead and convert units from SI to English units so that we would not only be able to use the information and data here, but also around the world. We also converted the cost from dollars to euros to the Chinese yuan. And as far as the global engagement, the fact that we were able to partner up with Hardware gave us a larger audience that we were able to reach, instead of us just working with us alone, instead of with Hardware. As for the environmental and social aspects, we made sure to go ahead and recycle properly our materials, such as the acrylic, which you'll be hearing about later with Danilo. And also the water that we use as the liquid medium, we made sure to reuse it. So each different test, we went ahead and reused the water instead of just wasting it. And here we have some of the standards that we did implement into the testing. The first one is the selection and characterization of the weather and reference. That has to do with which materials were chosen for which task and how we went about using them. The second one has to do with the temperature calibration. That has to do with how we went ahead and calibrating the pressure and temperature data. And lastly, we have this reporting uncertainty of test results. That has to do with how accurate our data was, how many significant figures were used, and
As far as the construction of our system, we actually had a few. We had a few procedures, and we actually had a few materials. So some of the procedures that we had were, for example, using machines to drill the holes and applying adhesive to some of the components in order to put them together. And we chose acrylic because acrylic was a good insulator, and on top of that it was anti-corrosive, so it allowed us to be able to work with water and other mediums. As far as manufacturing, with the help of Professor Cigarelli, we were actually able to write and use some of the machines like the CNC machine. We actually have this right here is a picture. It's supposed to be of a CNC machine actually drilling and tapping into one of our acrylic plates in order for us to fit our figures. Throughout our test picture, we actually had a few parameters in order for us to optimize our test picture. And for example, for temperature, we actually in the beginning for the first test we wanted to use a heating cartridge. The heating rod actually was supposed to thread into the plate. The problem with the heating rod is as we heated the rod, it was heating through the adhesive to the Teflon we were applying to it, so we were losing pressure inside the box. In order for us to maintain the pressure, we actually ended up using a recirculator. The recirculator allowed us to heat the water outside the box and feed it into and maintain a closed system. The closed system allowed us to maintain and keep the pressure while achieving the temperature we wanted. For us, in order to induce the pressure, we wanted to use a Varicom. The Varicom it's a pressure inducer. The problem with the Varicom was it wasn't enough to actually feed the system itself. There was too much area. So in order for us to feed that pressure, we used them both. The bulb, on the other hand, was enough to feed the amount of pressure that we needed, but it was inconsistent. We weren't getting a consistent amount of data every time we were feeding. In order for us to get that, we actually ended up using a syringe. The syringe allowed us to get a consistent amount of data and acquire the pressure we wanted inside the chamber. As you can see here, this is our final test rig with all the optimizations that we wanted to do, and a few added other ones. Right here, we actually have a disposable pressure transducer. The disposable pressure transducer reads the pressure inside the chamber and gives us an electronic feedback. Now, in order for us to read that, we actually assembled the DAC. The DAC was supplied by the company. All the components were supplied. The only thing is we had to go out and assemble. We had to solder, build, wire, and make sure that it worked. Now, in order for us to use the DAC, we had to use a PALDA system. The PALDA system basically read what the pressure transducer was reading back and gave us a time versus pressure graph continuously as we were reading our experiments. As you all know, we're working with pressure and temperature. Now, the problem with working with pressure is sometimes you get a small leak and you don't know where it is. So in order for us to acquire and check where we're getting the small leak and we were verifying, we did a water submersion test. Here, it shows us we had a small leak on one of the top of the chambers, which helped us allow and fix our seating. And now the testing, we actually tested from 20 to 60 degrees Celsius. We did this using in increments of 5 degrees Celsius. For every 5 degrees Celsius, we went from 0 to 200 millimeters mercury. This allowed us to get a broad and a good spectrum of data in order to provide back to the company. For our cost analysis, it shows us here the amount of money spent on the actual rig and the savings part of the company. The reason why the savings of the company was so high because we actually based our company, we decided we wanted to base our company on the fittings instead of the components. Now the fittings that we use for the test rig are threaded on one end and have a universal locking feature on the other. Now these fittings allow us to interchange the components between any different parameters, any different sections. We can actually place the components next to each other or separate them away. So it allowed us also to use the components that the company provided. And we didn't have to go out of our way to go buy separate components when the company, our fittings actually were universally available there for the company. This right here is actually a quote that the company got from another third-party company to build the apparatus that we actually built to them to test their sensors. As you can see there, our projector was actually supposed to be $5,000. We saved them about $4,700, and they were actually quoted $18,000 to build.
In order to validate our results, we perform a simulation study. Concerning the simulation study, we perform a static analysis first. So we impose the loads, mainly in terms of temperature and pressure. So what we wanted to do was make sure that the test rig was going to uphold those parameters specified. So we ran them, and we did 10% on top of that. So for instance, in temperature, the desired temperature of hardware was 60 degrees Celsius. We ran it at 66 degrees Celsius. We did the same in terms of pressure. It was 200 millimeters of mercury, so we ran 220 millimeters of mercury to certify. We also induced the weight of the liquid itself being water in the situation. For the Solidworks simulation, we obtained our stress results. So in terms of the stress results, in the top picture you will see the external stresses of the test rig, and in the ISO clipping on the bottom you will see the internal walls of the test rig. Both of them, through the yield, can be shown to have values way below the yield, meaning that the test rig resisted those stresses. The factor of safety that we obtained was a 5.4, meaning that the structural capacity of the system was 5 times stronger than the minimal capacity. For the displacement, we observed I'm sorry, it's just not running the proper way.
The open folder in the bottom left corner, there should be a local copy of everything. As opposed to the browser. Right now you're in the browser, so try with the folder in the bottom left.
Yeah, this is the
Well, the first video was supposed to elucidate how the displacement was going from the smallest pressures and temperature to the highest pressures and temperatures. So it could be illustrated how, for instance, at the highest temperature, it changed its color. Then in the second video, it showed the displacement of the external contours of the test rig, and the highest displacement obtained was still low enough, being of 5 hundreds of a millimeter, so the acrylic resisted those conditions. The temperature calibration was performed, and in order to do this, we used the uncalibrated sensor provided to us by hardware, and we also used a calibrated temperature thermometer provided by hardware as well. So we ran in a closed loop the experiment, and we did from 20 to 60 degrees Celsius in increments of 2. Then we obtained an offset of 0.4 degrees Celsius, and these results were also implemented for a pressure analysis. In terms of the pressure analysis, this table is a summary of the experimental data that was acquired. There were 10 repetitions of the experiment in terms of the different temperatures we analyzed, being from 20 to 60 in increments of 5. We cut the sections, and this is only a minimalization of the data. And then after that, we used the program JUMP to perform a statistical analysis. So in terms of that, we did the mean difference, and we did the meaning the mean from point to point of each of the experimental data acquired. We also analyzed our correlation of 0.99, identified that it followed a linear regression pattern. After that, we used MATLAB to perform the actual calibration of the temperature and pressure sensor. So in order to do this, in the first step, we did the slope modification, as you can see. And then after the slope modification was performed, we did the offset. These results were implemented in the calibration table that you're about to see. And then we performed, and then through the linear regression, you can see how the data actually fitted that linear proportionality. This is a summary of the data of the calibration table we gathered. And so the slope modification is represented as well as the offset in millimeters of mercury. We represented it in bar graphs for you to have the visualization of seeing that through linear interpolation, it would be possible for the company to also induce other values for temperature and pressure as desired. So it can be seen that as the temperatures increased, the pressure was also, for the slope modification and the offset, were increased as well. The residuals were considered before calibration and after calibration. So before calibration are the values in blue, and after calibration are the values in red. So before the calibration, the residuals, the mean residuals were of 11.3, and after the calibration was performed, it was of 1.1. We wanted to verify that our calibration was actually accurate, so we tested our prediction. We ran again the same experiment, and we tried to predict what would be the values read by this sensor once the calibration was done. It was identified that the percent error was 0.83%. For lifelong learning, we definitely learned about team cooperation, effective time management, and we applied all the engineering principles gathered to our undergraduate to solve intricate problems and solve our problems in creative forms. We would like to, throughout our professional careers and work ethic, continue applying the experience and knowledge that was gathered through this project. In conclusion, the calibration table was accomplished using linear regression, illustrating linear regression, and through linear interpolation, more values could be obtained for the company's usage. And then the test regression was performed effectively, showing residuals of 1.1 and a percent error of 0.86%. The company's savings were of around $5,000, that is excluding the quote provided by hardware itself of $18,000. Right now, the company is actually using our test rig, therefore we don't have it here today. And for the future work of our project, we would like to implement different mediums such as glycogen or blood itself to see how the calibration could be modified, and we would like to use different equipment itself to verify the legitimacy of our calibration. Thank you.
It's your test rig that you built that is now being used by them, which is pretty cool, actually.
Yes, definitely. They had their trip using the sensor too.
Which is too bad because we don't get to see it. But are we looking at it in this?
No, that was just a preliminary. It was just a picture we found when we were first trying to do it because we didn't have a sense of what we were going to do yet. And we actually ended up building. They have two that they're using right now. We had two different models we had to build because they wanted a second one just so they could induce the pressure and induce the temperature and basically show partnering companies that they could provide basically a calibration table and a medium, say for example. And then they have the other one where they can actually input sensors into it. So they actually had to go out of the way and build the second one because, you know, they wanted a second parameter, which we actually liked. We got more information on it.
So it started, the project was to build one and you built two.
Yeah.
Well, the project itself was to optimize it.
Yeah.
So if we had to build 10 different ones to ultimately come up with the best project, it would have been like that. In this case, it took us basically 3 trials.
Mhm. And we used each, everything that we found in each one to make the next one better, in turn optimize.
So are you all done or are you going to go after another one?
Well,
Well, I actually got a job there. I'm working there now. So,
Oh,
today I was actually, when I was leaving, because I told them after the presentation, they're like, oh, okay, well, later we got to talk. We actually have some ideas for it. So I'm not getting away from it anytime soon. They're actually telling me to optimize it even more. Put
Can
more
we
stuff
come
into
over
it.
and get our heart checked?
We can make that happen. We can make that happen.
Okay.
Good.
Any more questions?
All right, thank you very much.